Alright, looking at the lecture, physics is transcendental. The quote we have is, "Science does not know its depth to imagination," by Ralph Waldo Emerson. What we're trying to do in this presentation, what we're trying to learn, students should be able to recognize the importance and apply the rules for proper measurement. So in physics, we're going to measure things with different measurement tools, and we should be able to apply those rules for everything to look at accuracy and precision. Students will be able to convert between different systems of measurement, being able to convert between using a meter, yardstick, being able to look at all the different types of volumes, mass, looking at kilograms and grams, balances, all that stuff. Students will understand the purpose and be able to apply scientific notation. It's very important in physics because if we have some really big numbers or some really small numbers, we need to be able to put them into something that's manageable, which is scientific notation. And the fourth thing, students will understand the origin of algebraic formulas and successfully manipulate them. Very important concept in physics, those algebra. It's very key in this, and so getting our base in algebra is very important. Now, in physics, we have a ton of equations. We actually have your formula chart will be a very good, useful place to look for things. There's an equation pretty much for everything that we use. So after this, we'll talk a lot about, and next lectures to come, we'll talk a lot about equations that we use. Algebra is very useful in representing the relationship between those variables. The reason why we want to use algebra, why we want to use these equations, is because it allows us to examine these relationships without performing an experiment for every situation. So instead of looking and we're throwing a projectile, we're throwing a ball up in the air, if instead of having to throw it every single time to see what the height is going to be, if we know what the initial velocity is, we know some other variables, we can calculate the height that it's going to go. So it makes our life a lot easier. We don't have to do an experiment for every single thing. Now, how we rearrange equations. And usually in physics, what we're going to get is that when you mess up, you'll mess up usually on the algebra portion of it. And so learning the algebra helps us out a lot. And these are some simple steps that we can take to rearrange our equations to solve for different variables. So the first step is we look at the equation and circle the variable we want to isolate. Here we're circling our delta D, which is going to be our change in distance or displacement when we're looking at that. So that's what we want to isolate, and we see that we've circled that. The next step is the variable of interest must always, and this is very important, always be in the numerator. So it has to be, if there's a fraction, it has to be in the numerator. So therefore, to get this in the numerator, since our original equation we see that we're dividing here, we multiply both sides by delta D, and we see that it eliminates, it cancels out. So after we get, if it's not already in the numerator, we put it in the numerator. The next step that we do is we continue to isolate your variable of interest. So if we look on the other side, what we ended up with, we had acceleration times our delta D. Well, we got to get delta D by itself. So since it's multiplying here, the opposite of that would be division. So we divide both sides by A, which is our acceleration. And then we finish when your variable of interest is the only thing on one side. So we see that we have what we wanted all by itself on one side, and we've successfully rearranged. Okay, example A1. It says rearrange the formula to isolate for D. So we're isolating for this. One thing right here, realize that what we have down here is D squared. So we'll have to do something a little different at the end for this one. But let's follow our rules for what we're going to do. It's on the denominator right now, so it has to be in the numerator. So we go ahead and we multiply both sides by D squared. Okay, so we multiply both sides by D squared, and what we see is going to happen is that we'll get rid of D squared on the bottom. It goes away because it cancels out on this side, and we're left with an equation that looks like this. Now, from here, all we have to do is we have to, again, continue to rearrange so that we can solve for d. So the next step that we have to do is we have to get our f of g to the other side. So we go ahead, and it's multiplying here, so we're going to divide both sides. We'll make it a little smaller. Divide both sides by f of g. We have f g on this side. See, it cancels right here, so that's going to go away. Okay, so that f of g on the left side goes away. And all that we are going to be left with on the left side is just going to be d squared, but we're not finished. Normally everybody wants to stop right here. They go, oh, we got d by itself on the other side, but this isn't d, it's d squared. So what we have to do is we now have to solve just for d. Well, how do we get rid of a square? We square root both sides. And what that'll do is that'll take care of that d squared and turn it just into d. And we see that this will be the equation that we use to solve for our distance. Okay, guys, on this one, it says, example A2, it says rearrange the formula below to isolate for our VF, or that would be called our final velocity. Some helpful hints here. Think of this numerator as in parentheses, and you want to get the delta t to the other side first, and then isolate just for your VF on that one. Okay, let's see if we can't get that answer right, and we'll talk about it later. Alright, this is example A3. It gives us the formula for density. Density equals mass divided by volume. The answer that you should get, because you're going to be solving for mass, rearrange the equation to isolate for mass equals density times volume. You should be able to tell me how to get that answer. Okay, let's look at different forms of measurement. The first one is length. We also call this our distance or our displacement. It's the fundamental unit of measure. It's one of them. It's the distance between 2 points in space. The standard unit for it is going to be in meters. And the way we define it is by how far light travels in 299,972,458 of a second. And so that's how we defined length. Time, it's a fundamental unit of measure. It's the interval between two events occurring. The standard unit, and that's important, is seconds. And we see that it's defined as how long it takes for 9,192,631,770 vibrations of a cesium-133 atom. Mass is a fundamental unit of measure. It's the amount of matter in an object. One thing I would note here, mass is not weight. The standard unit is kilograms, and it's defined by the standard kilogram. And then we have temperature. Temperature is another fundamental unit of measure. It's the average molecular motion of a particle. You could also say it's the average kinetic energy of a particle. The standard unit for this is Kelvin. It's a scale that we measure everything in science in. Our normal thermometers are going to be in Celsius, but the standard unit for temperature in science and calculation is going to be Kelvin. It's defined by a point at which all molecular motion ceases and the triple point of water. And so that's going to be our definition of temperature. Okay, starting with example B1, it says, what is the volume of an object shown below? If we look at the object, we can see that it is going to be a cylinder. So the equation for the volume of the cylinder is volume equals our radius squared times pi times our height. And so here all we have to do is, this is telling us our diameter, so we divide that in half and we get our volume is going to equal 1.5 squared times pi times 2, which is our height. And we should get an answer right around 14.414, and that would be meters cubed. Okay, example B2, it says, what is the volume of the object shown below? What you can see in the picture is actually a Rubik's Cube. So the volume, the equation for the volume of a cube is just one length of the side cubed. And the one thing that when you're looking here to find out what the length is, you're measuring in inches, and it's okay to leave it your answers in inches cubed. So look, figure it out, make sure that you read the ruler correctly, and then cube it. Okay, example B3. When we're looking at this, you should get an answer right around 13.8 centimeters. And I'll zoom in. You're just trying to find the length, and I'll zoom in pretty good so that you can get a good look at the meter stick and realize that these numbers are going to be your centimeters. Okay, looking at units and looking at matter, we looked at this in our Engage. It says, but units don't really matter, right? And we looked at the Mars Climate Orbiter, and we see that the ground software used English measurements and the onboard software used metric. And what we saw was the cost of the orbiter was right around $330 million. And it crashed because they didn't convert correctly. They weren't in the right unit. And it crashed with all loss of material and instrument and data. We also look, anytime, we're going to use conversions throughout your life. You're going to use it anytime you need to convert money. Say you go overseas and you need to convert from dollars into a different unit of currency. Those units matter. Okay? You got to make sure that they're not taking advantage of you and everything else. And you got to know what type of conversion factor you're going to get for that. So units are very important even beyond the scope of this class. Okay, why do we convert? Number one is the measurement can't always be done in standard units, measuring circumference and diameter. So when we're looking at those things, they can't be done in standard units. The other thing, if we're working in, say, we're measuring something very small, we want to be incredibly accurate and precise with it. We'll use a gram balance instead of having it in a kilogram balance because it'll help us get more precise with it. Another reason is the fundamental constants are often used in formulas requiring standard units. Basically the same thing that I was talking about. You've got to have it in kilograms when we were talking about working things out. So we got to have that. Okay, some common English conversion factors. So things that we'll use, we see that length, that 2.54 centimeters equals 1 inch. We see that 1,609 meters equals 1 mile. Temperature, and we see we have temperature here going from Fahrenheit to Celsius. Time, 1 hour, and this is really important because we measure things in physics. We'll use meters per second, but when we measure things, usually it's in miles per hour. So we got to take it from hours to seconds. That's an important one. And we see that mass, 2.2 pounds equals 1 kilogram. So those are some real important English conversion factors. Now, some metric conversion factors. And the metric system is based off of a system of 10. Okay, so everything is 10 above the next. So our base unit, what we're going to have, our base unit, when we're going to have kilo, kilograms, grams, and we're looking at that. The base unit is always going to be grams, seconds, meters, and all of these. And so we can go up or we can go down from that. So we see that we have our nano, micro, milli, centi, kilo, mega, giga. And so they give us the variation of those. The base unit that we always have, we have over here. So our base unit for our mass is going to be grams, and then we go up to kilo, which is 1,000 times greater. Or if we go down to milli, we see that it's 1,000 times less. Okay, and so the base units that we always have will go up and down from there depending on 10. Okay, example C1. It says a car travels at 80 miles per hour down the highway. How fast is it in standard metric units? Okay, so we're in miles and hour, miles per hour. What that means when we look at it, it's 80 miles in 1 hour. So if you're traveling 80 miles an hour, if you travel for an hour, you're going to travel 80 miles. And so the conversion factors that we need, and we call these statements of equality. So we want to go from miles to meters. So we know from what we just wrote down that there are 1,609 meters in, which equals 1 mile. Okay, and then it's in hours, and we need it in seconds. So we know that there are 3,600 seconds in 1 hour. Okay, those are the conversion factors that we're going to use. And you probably saw this in chemistry. You probably use it a lot. If you haven't, and this first time you've seen it, then it'll look a little different. But the way we set it up is all we have to do is we set up our conversion factors so that the units cancel each other out. So if miles is on top, we have to put miles on bottom. So all we have to do is come over here, put miles on the bottom, and then we put the other half of the equal sign, the other half of the conversion factor on top. Okay, and what that will do for us, since miles is here and miles is here, it cancels out. Now we're in meters. Okay, but we're not done because this is meters per hour, and we don't want that. We want meters per second. So we keep going. Same thing that we have to do. Hours is right here, so we got to put hours on top. So we put our 1 hour on top, and we put our 3,600 seconds on the bottom. A little jumbly there with the words, but we see that we have it set up and what it looks like that. And we should get an answer right around, if we multiply 80 times 1609 times 1, all divided by 3,600 seconds, we'll see that we will get right around 26.8. And our units will be meters per second. Okay, example C2, it says a weightlifter is capable of bench pressing 250 pounds. What is the mass in standard units and standard metric units? The hint that we can get here, we need a statement of equality. We need a conversion factor. So it's 2.2 pounds equals 1 kilogram. And that's what we're going to use. Start with this 250 and go ahead and work that one out and see what answer you get. Example C3, it says determine the distance in standard metric units of a marathon, which is 26.2 miles. We've already used the conversion factor for this before. The answer that you should get is 42,200 meters. You should be able to tell me how to get that answer. Okay, scientific notation. What scientific notation is really useful for, how it helps us, is that scientific notation, the Earth, if we're looking at the Earth's mass, the Earth has a mass of 598 and it has a ton of zeros behind it. Or if we're looking at the mass of an electron, we see that it's a very, very small number. And so what scientific notation allows us to do is scientific notation allows us to take very big numbers and very small numbers and put them into a manageable number, something that we can actually see and use without having a huge number on our page. When we're looking scientific notation rules, the format that we have for it is that M must be a number greater than 1 and less than 10. Basically what this means is this M number, the variable that goes in front, you can have it be 1.5. You can have it be 9.8. but you can't have it be 0.5. That's not between 1 and 10, and you can't have it as 10.1 because that's above it. Okay, it has to be somewhere between 1 and right around 9.99, so on. It has to be between that. N must be an integer, meaning it must be a positive or negative whole number. Can't have n, which is right up here. It can't be 1.5. Can't be 3.6. It has to be a whole number. It has to be an integer. And it can be positive or negative. Now, n is determined by the number of places the decimal must move to make m a number between 1 and 10. Okay, so when we're moving, like with our big numbers, when we move the decimal, that is what n is going to be. What I would write here, determining if it's negative or positive, positive numbers are really big. So if it's a really big number, n is going to be positive. If it's a really small number, n is going to be negative. Now, example D1, it says a cesium-133 atom vibrates 9,192,631,770 times in 1 second. It says determine the time of a single vibration in scientific notation. So if it vibrates this much in 1 second, what we have to do to calculate that is we go 1 all over 9,192,631,770, and we go ahead and we plug that in the calculator. And what we should get is we should get a number of 0. And we have 9 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, and that would be 108. Okay, or 1088. That is what we get. That's how much it takes to vibrate 1 time in seconds. So we want to put it in scientific notation. Now remember, we have to move the decimal over enough places to get a number between 1 and 10. So we go ahead and we move it over. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if we move it over 10 spaces, we'll get 1.088. Okay, and then we put times 10. Now remember, n, it's how many times we moved it. Well, we moved it 10 times. And then we have to say to ourselves, was it going to be positive or is it going to be negative? Remember, the positive numbers are big. Was this number big? No, it was small. So therefore, it'll be negative. So our answer should be 1.088 times 10 to the negative 10 seconds. Now, an astronomical unit, or AU, is the distance between the Sun and the Earth, which is 150, and that would be billion meters. Express this value in scientific notation. Okay, remember here, you have to move the decimal to get it between 1 and 10. Remember that how many times you move the decimal, that's going to be your n value. And then you ask yourself the question, was it big or was it small? If it's big, it's positive. If it's small, it's negative. You should be able to get the answer on this one. Now, example D3. Your physics teacher tells you that your grade is 9.6 times 10 to the 0. What is your grade in the class in standard notation? So what is it in simple units or simple numbers? When we're looking at this, the answer you should get is 9.6. You should be able to tell me the reason why.